Bismillahirrahmanirrahim. In today's tutorial, we'll be talking about ideal gases. We'll start with the ideal gas law and we'll solve a couple of problems from sheet 1. Alright? Okay, so what's an ideal gas? We have two assumptions for a gas to be ideal. First off, the volume of the molecules is neglected compared to the container the molecules are in. So something like this example on the left. We have just these two molecules, and compared these spheres or molecule volumes compared to the total volume of the container, this square they're in is neglected, or could be assumed that it's zero with respect to the total volume of the container. The second assumption is that there are no forces of interaction between these molecules. It's like the molecules do not see each other and do not interact with each other. And again, if we have something like this example on the left, then we could safely assume something like that, because the total volume is very big in comparison to the volume of the molecules, and the molecules have very minimum chance of interacting with each other or meeting each other in that container. This is as opposed to the example to the right, where we have too many condensed molecules in the container. So we cannot ignore all the total volumes of the molecules here in comparison to the total volume of the container, because they take up a decent percent of the total volume. And of course, since they are so close together, we cannot neglect the interaction forces between them. They will interact with each other, and there will be some electrostatic or intermolecular forces between them, whether they're attraction or repulsion between the molecules. So this is an example of how they would move inside the container. As we can see, these two molecules have very minimum chance of seeing or interacting with each other or colliding with each other. But in this container, the container is too condensed with the molecules in it, so they will interact and they will collide often with each other. Okay. All right. In real life, when can we treat a gas as an ideal gas? First, we can have high temperature or low pressure or both, to assume that we have the case on the left in here. Okay. All right. So starting to build the ideal gas law, how do we quantify or relate the parameters of the gas together? What are the parameters of the gas? These are the temperature, pressure, volume, and amount. And the amount is the number of moles. We represent the amount by the number of moles. So the first scientist to start hypothesizing or forming a relation was Boyle, and he studied the relation between the volume and the pressure, okay, and fixed everything else. So amount and temperature are fixed. We'll start studying the effect of pressure on volume and vice versa. So in this piston cylinder setup, we have the volume grade in here, and we have the pressure as weights on the piston itself, and the volume of the gas is in here. Okay, and temperature and pressure gauges to know how the pressure and temperature change inside this piston. Inside the cylinder, sorry. Okay, so we found that the more we add some pressure in here, the less the volume becomes, and vice versa. If we release or remove some pressure from the piston, then the volume expands. And this can be actually shown in this animation. The more we add some weight, the less the volume becomes, and vice versa. So the final relation we can get from here is that the pressure is inversely proportional to the volume, and the pressure times the volume is a constant, and this constant is actually we can assume that this constant is a function of number of moles and temperature, since we have them as constant values in here. We didn't change them, so it will be a constant if we fix both these values. If not, then it will change. This constant will change. All right. Going forward, Charles was the second scientist to formulate a relation, and he studied the relation between the temperature and the volume at constant amount and pressure. Okay, and he found that the more we increase the temperature in here, let's say we have a flame in here, the more we increase the temperature, the more the volume of the cylinder gas here becomes. It expands, and this is actually logical. We add or introduce some heat into the system. The heat is absorbed as energy, internal energy. For that gas, it increases the kinetic energy of the molecules and they expand. Okay, so if we go and see the animation, the more we increase the temperature, the more the volume of the gas becomes. Okay, so we have the second relation here, is that the volume is proportional to the temperature, and this constant will also be a function of number of moles and pressure. So at a constant number of moles and pressure, this constant will be a certain value, a constant value. If we change the parameters here, this constant will still remain a constant for these conditions, but it will be a different value for the new conditions. Okay. The third scientist was Lussac, and he studied the relation between temperature and pressure, and of course setting the number of moles or the amount and the volume to constant values. Okay, and we found that if we keep the volume constant and add some temperature or add some pressure, the volume or the pressure or the temperature increase on the other side. So let's say in here, let's see this animation. The more we add pressure at the same volume, the temperature increases, or the more we add temperature here and we want the volume fixed, we'll need to add some more weights to keep the volume fixed at a constant value. Okay, so the relation we came up with here is that the pressure is a constant times the temperature. And then the last relation we'll talk about today is the Avogadro's relation, and he studied the relation between the volume and the number of moles or the amount inside that container, so fixing the temperature and pressure, and we found that the volume is directly proportional to the amount of molecules or moles inside the cylinder here, and this is done by injecting some molecules by this piston, or getting out some of the molecules in here. Okay, so the volume is directly proportional to the number of moles, and this constant is a function of temperature and pressure. All right. Okay, so combining all those rules together, or these relations, we can come up with a relation that says P, the pressure times the volume, is always constant, and it depends on the number of moles and the temperature, and this constant is termed the ideal gas, universal gas constant. And for the values or the units that we'll be using in this course, the value will be 0.082, and if we see from the above relation, if we get R in the left hand side and get everything on the other side, so this will be PV over NT. So the units of, or dimensions of the universal gas constant will need to be pressure, which is atmosphere, volume, which is liter in here, number of moles, which is moles, and then temperature, which is the Kelvin unit in here. Okay, so just remember this. To use this value, we'll need to use these units when substituting into this ideal gas law or relation. Okay, and to get the Kelvin or the absolute temperature from the Celsius degrees, we just say that the temperature in Kelvin is equal to 273 plus the temperature in Celsius. Okay, and that's it. Alright, so let's start solving some problems. The first problem says a container has a capacity of 10 liters, so we have the volume in here, is filled with a gas at 2 atmosphere, so the pressure, and 0 Celsius, this is the temperature. At what temperature the pressure inside the container reaches 2.5 atmosphere. So this will be P2, and let's say this is V1, which is also V2 since the same container is used in both cases, and this is P1 and this is T1. Okay, so if we think about this, substituting 2 times in the ideal gas law for the different 2 conditions, we'll find that everything else is constant, the number of moles and the volume of the container, since it's the same container. The universal gas constant, the R, is also constant. So we'll have P1 equals T1 over P2 equals T2. And the only thing that's not known here is T2. We can calculate that simply by substituting, and don't forget to convert this to Kelvin, so it's 273 plus 0, which is just 273 Kelvin. Okay. The second problem, calculate the pressure of 0.25 moles of nitrogen gas that has a volume of 10 liters and 100 degrees Celsius. And this is just direct substitution into the ideal gas law. We need to know the pressure and everything else is given. So we just 0.25 is the number of moles, 0.082, this is the universal gas constant, 373 is just the 100 Celsius but in Kelvin. Okay, 10 is the volume in liters, and we get the pressure after that. Okay, the third problem, calculate the volume of 5.1 grams of vapor of a material having a molecular weight of 114 grams per gram mole at STP. What does that STP stand for? This is standard temperature and pressure. So the temperature here is, the standard temperature is 273, which is 0 Celsius, okay? And the pressure is just the atmospheric pressure, which is 1 atmosphere, okay? So we want to get this volume, but we don't have the number of moles ready yet, but we have the grams, which is the total mass, and the molecular weight for that gas. We can easily get the number of moles by dividing the total mass by the molecular weight to get the number of moles, and then substitute in the ideal gas relation or ideal gas law to get the volume for that gas. Alright. The next problem says, what's the temperature of an ideal gas that has a concentration of 1 gram mole per liter at 1 atmosphere? So here, if we try to use the ideal gas law as it is, we don't know either the V or the N or the volume or the number of moles, but if we look at this quantity here, it says 1 gram mole per liter, so we know that this is actually the concentration is actually the number of moles over the volume in here. From the units, we can know that this is a unit of number of moles, and this is a unit of volume. Okay. So substituting by this C into the ideal gas law, we get that P equals CRT, and we can just get the temperature from there. All right. Next problem. In this problem, we have an air that's compressed at 50 degrees Celsius and 750 millimeter mercury. So this is the temperature and this is the pressure. Then mixed with 10 grams per minute, 10 kilograms per minute of ammonia. So let's say this, since it's a flow rate per unit time, we give it the dot notation here. So that the proportion of the gaseous mixture molecules is still mixed, and here is the composition of the outlet gas. Okay, calculate the exit air rate from the compressor and meters cubed per minute. So first off, let's start by plotting or drawing the system. We have air that's coming out of a compressor. Let's draw the compressor in here. Okay, this is a compressor. And this is the ambient air. Okay, so this compressor takes ambient air and compresses it at these conditions, temperature and pressure, and we want to get this V dot. Alright, that's going into the mixer and coming out of the compressor to be mixed with the ammonia, the 10 kilograms per minute of the ammonia, to get a mixture of this particular composition. Okay, so where did the nitrogen and oxygen come from? These two are actually the air, but just split out into the components of the air. We always assume that the air is just like 80% nitrogen and 20% oxygen. Okay, so this is actually saying that the mixture has 85% of air and 15% of ammonia. Of course, and this is in mole percent. Okay, if it doesn't say in the problem that otherwise, or that this is a mass or weight percent, we can assume that it's by default mole percent. Alright, so how would we solve a problem like this? We don't know here if we try to use the ideal gas law and we want to get the volume. We have the pressure and temperature, but we do not have the number of moles of the air coming outside of the compressor or going into the mixer to substitute in here. So the first thing we need to think of, where in this system, where can we relate this number of moles of air to anything else? And in this particular system, we have this composition. So we know that for each 85% air moles, we have 15% of ammonia moles as well. So we can say that number of moles of air over number of moles of ammonia is 18 over 15, and we can just get that ammonia to the other side to get the number of moles of air into a side by itself. Okay, and once we get this number of moles of air, we can just substitute into the ideal gas law and get the volume of the air. All right. So and of course, just a quick comment here. We're using the ideal gas law with the dot notation since this is not a static container that just contains some volume in it and that's it. We have a mixer and we have streamlines, these ducts or pipes that transfer the gases. And we can also describe the gases by the ideal gas law, but this time we'll take into account that they are flow rates and not just static values or static system. So it's like we just divided the entire equation by the time. So the volumetric flow rate of the air, how many liters per minute are going into the mixer, for example, are related to how many moles of that air are going into the mixer. Okay, so we can just use the same law, just dividing by the temperature, by the time. Sorry. Okay, so the second thing here is that we still don't have the number of moles or the molar flow rate of the ammonia, and that's the second problem. But if we think again about where in this particular system can we get a relation to get this number molar flow rate or number of moles, we can see in this given that the ammonia flow rate in mass is 10 kilograms per minute. So we can relate the molar flow rate for ammonia to its mass flow rate by just calculating the molecular weight for that ammonia gas and do not forget to convert kilograms to grams. Okay, and in this step we can get the molar flow rate for ammonia, and then go back and substitute here, get the number of moles for air or the molar flow rate for air, go back to the first step and substitute in the ideal gas law to get the volumetric flow rate for air. So let's remove all the comments in here. So that's how it goes. This will be calculated first, then this calculated second, and then this is the last step. And once we get the volumetric flow rate for air, the units we're working with are liter per minute, and we want it in meter cube per minute, so we just need to convert it into meter cube per minute. Okay, and that's it for this problem. The next problem, we have two containers. The first container has an ideal gas A, and the second container has an ideal gas B, where the density of A is double the density of B. Let's show the ratios in here. And the molecular weight of A is half the molecular weight of B, and the two gases are at the same temperature. All right. Calculate the ratio of the pressure for gas A with respect to gas B. So, in this problem, if we try to work with the ideal gas law that we know, we do not have the volume or the number of moles or a relation to just relate those to, like the concentration in a prior example. So we have a second form for the ideal gas law that it's probably better for you to memorize it to be able to solve faster. And it's just breaking down the volume and number of moles into mass over density for the volume and mass over the molecular weight for the number of moles. And from here we can just take these out, the masses, and we end up with this rule. And this rule, this is the one that you need to memorize to be able to solve faster in the exam. So the pressure times the molecular weight is equal to the density times the universal gas constant times the temperature. Okay, and for that particular relation we can find everything in here, and we need to get this pressure ratio actually. So just substituting this relation 2 times for the two conditions, we can isolate P1 over P2 in the left hand side and calculate the ratio, which will be 4 at the end. Okay, all right. The next problem, a tank has a volume of 11 liters, contains 20 grams of neon gas and unknown weight of hydrogen. All right, so this is the mass of neon, and this is the volume, and we don't know the mass of hydrogen. All right. And the density of that mixture, so the density of the mixture, the total mixture, is 0.02 grams per centimeter cubed at 0 degrees Celsius. So this is the temperature. Calculate the following, knowing the molecular weight of neon is 20, of course, grams per gram mole. Alright, so the first thing we need to know is the moles of hydrogen in the mixture, then the average molecular weight, and then the pressure. Alright, so the mass of the mixture is just the density times the volume. We can get the mass as total mass is 22 grams. And we already know that neon is 20 grams in the system. So to get the hydrogen mass, it's just the difference between the total mass and the neon mass, which is 2 grams. To get the number of moles of hydrogen, we just need to divide this mass by the molecular weight for hydrogen gas, and don't forget that the hydrogen gas is diatomic. Total molecular weight for hydrogen is 2, 1 times 2, okay? And for the average molecular weight, we have the total mixture has 22 grams as the total mass, and the total number of moles in that mixture is 2, so the average molecular weight is just 11 grams per gram mole. Okay, just a quick comment here. For the molecular weight, we cannot just say the neon is 20 and the hydrogen is 2. So just get the average between those instead of getting the total mass over the total number of moles. That's because for the molecular weight, what we need to do or take into account that if we have a container that has one of neon and another one of hydrogen, okay, and we want to get an average molecular weight, this just means that we want to convert all the gases in here to gas X, and this gas X needs to have the same standardized or uniform molecular weight for each of the molecules in here. So if this is 20 and this is 2, we want a gas to give us the total, the same total number of moles and same total mass for the system, so that it has all of the other parameters for the same gas at the same conditions, of course. So the total mass in here would be 22, and the number of moles will be 2. So this is the mass and this is the number of moles. Here we also have 2 molecules, so the number of moles is 2, and we want the total mass to be 22 as well, so that we didn't change the system, we only just substituted the different gas molecules with just one standardized gas. Okay, so in this particular example, we have the total mass over the total number of moles gives us 11 per 1 mole of that gas X, the average molecular weight. All right. So anytime that we have the same amount of both gases, we can get the average between them. But what happens if we add another hydrogen atom in here, which is also 2? So this becomes 24 instead, and 3 moles instead of 2, and this will be also 3, and we need to have another gas X to give us a total mass of 24. This time, for each of those X's here, we need each one of those to be 8, right? So that the total mass would not change and still remains at 24, like the original system. Okay, so that's how we get the total number, the average molecular weight, by just getting the total mass and dividing it by the total number of moles, so that we do not change the system in any way. We just represent every mole in the system with a different average molecular weight or standardized molecular weight. Alright, and for the pressure, that's just direct substitution into the ideal gas law, and we can get the final pressure. Okay. The next problem, we have a gas mixture has the following weight percentages for its components, and we have the composition in weight percent. Alright, and all our calculations are in mole percent, so we'll need to deal with this weight percent first before doing anything to calculate any of the requirements. So the requirements are: calculate the density of this gas mixture at a certain pressure and certain temperature. Okay, so we need the density, so PM equals rho RT, and we need this rho from the relation, but we don't have the molecular weight, and since this is a mixture, we need to get the average molecular weight that represents all of the different gases inside that mixture. It's like we have this gas X as we just discussed in the last slide. Okay, so we need to get the average molecular weight of this system, but this system is in weight percent. We need to get the number of moles to know the molecular weight or total mass over total number of moles, like we did before. So we'll need to convert the weight percentages into a mass percent. So what we'll do is we'll just take 100 grams of that gas as a sample to know for that 100 grams sample how many moles are in there in that particular sample. Okay, why 100 grams? Just as a simple number to make the calculations easy, but you can pick any number, or you can even just work with M total, and then you'll find that the M total gets disappears in the end in the mathematical substitutions. Okay, so we have these two as the givens. These are already given here. I just wrote them in a table format, the component and the weight percent. For this basis of 100 grams, we have 80 grams of methane and 18 grams of ethane and hydrogen 1.25 grams. And we can calculate the molecular weight for each of these gases. So 16 for the methane, 30 for the ethane, and 2 for the hydrogen. And then the number of moles for that particular sample in those 100 grams is just 5 moles for the methane. It's just 80 over 16. And then same goes for the next or the other components. And then this is the total number of moles for a total mass of 100. So if you've taken like 1,000 for the grams, everything will be multiplied by 10, and this will be 62.5 instead of 6.25. So it doesn't really matter what number you take as a sample. It will still remain the same ratio in the end. For that X amount of grams, we have that X or Y amount of number of moles. Okay, so the ratio will always be the same, 6.25 over 100, no matter what number you take as a sample in here. Alright, so we do have the total mass and the total number of moles. We just need to divide them and get the molecular weight average for that particular mixture, and get the density from the rule above. Okay, let's do something here. Let's assume that we have M total, so that you're convinced that it doesn't matter what number we take. So this will be 80 M total instead of this will be 80%, percent. Okay, and if we take the M to be M total in here, alright, so it will be 80 times M total, 18.75% times M total, and 1.25 M total. Of course, these are all percentages, so they are divided by 100. Okay, to give us in the end one or a total of M total. Okay, and in here we will have this expression divided by 16, so it will be 5 over 100 of that particular M total, and so on and so on. Okay, so this will be 6.25 over 100, since it's a percent, times M total. So when we get the molecular weight, we'll just say the molecular weight average will be just the M total sample that we've taken, or the total mixture, over the 6.25 over 100 times the M total, because this parameter carried over with us. So it will be just 100 over 6.25, which is the same value in here. Okay, that's it for today's tutorial. Please let me know if you have any questions. See you next time. Cheers.